Well, hi guys. We're going to do some arc length. I want to teach you this. I want to develop the formula for arc length, and I also want to work a few examples. And then tomorrow in class, you guys will be able to do your work in class. And this will be our last topic for Chapter 7. And so let's just get after this. Let's first of all develop our arc length formula, and I want to show you where it came from, and then we can get after some of the examples. So let's give me a little marker here. Take and get a little axis here. I've got to use a little notebook to keep my thing steady. There we go. All right. So we're going to do arc length, and let's just say that I had a graph started here at A and went out here to B, and it was curvy. And it did something like this. All right. Now, one approximation to the length of this curve would be of course, the shortest distance approximation, which is the straight line approximation. Now, the length of that straight line is an approximate distance for this, and of course it would be an under approximation. And what we could do here is just the Pythagorean theorem. We could find out what our change in y was. Oh, I don't want to have that marker there. I want to have this one. Sorry. We could find out our change in y, and then our change in x, and we could just do like maybe the Pythagorean theorem here, but the length of that curve would be the square root of my change in x squared plus the change in y squared, just the Pythagorean theorem. And of course this is too short. That is an under approximation. So what could I do to make this a better approximation? Well, I could maybe break this into pieces and say, well, what if I did two straight lines? So what if I did this first one and then that second one and added those up? So then the sum of these two you can see is a closer approximation to the actual length of that curve. Get back to my marker here. So my length would then be the sum of these two. So I would have the square root of that first change in x squared, the first one, plus the second change, or the first change in y squared, and I would add to that my next length of my next line segment, which is my delta x sub 2 squared plus delta y sub 2 squared. So I could have the sum of those two. And of course, if that's not good enough, then I could do more. I could pick some more points in here, and I could find the length of this line, the length of that line, then the length of that line, and the length of that line. And then I'd have four things to add up. And so you might see where we're going here. We're heading towards a summation. So I would end up adding up. From 1 to n, however many of these that I wanted to do, of the square root of all of these delta x sub I squared plus delta y sub I squared. So I would add all these up, and this is starting to look like a Riemann sum. And if I wanted this to be a Riemann sum, I'd want to make n go to infinity, but I'm missing something. With a Riemann sum, we typically have a delta x out here on the outside of some function height. So what I can do is I can factor out a delta x sub I squared. So let's take a look at what that looks like. If I have my summation from 1 to n, open up my square root. If I factor out a delta x sub I squared, what does that leave? That leaves a 1 plus delta y over delta x sub I squared. Hi, 1 second, I'm making a video when you just came in here. And okay, we just had a visitor come in. Anyway, hi. That's all right. And so where was I here? I factored that out. Okay. And what this allows me to do is I can take the square root of both of these, and so I can turn this into this Riemann sum that is the square root of 1 plus delta y sub I over delta x sub I squared. Then I've got the square root of delta x sub I is just delta x sub I. Square root of delta x sub I squared is. So now I have a Riemann sum, and if I let my n go to infinity, then I have a infinite Riemann sum, and I'm going to turn this into the integral. And we end up with our formula for arc length. And that formula is the integral from a to b of the square root of 1 plus. Now, what does delta y over delta x squared become through the limiting process? That becomes dy over dx squared, which is our derivative. And delta x sub I becomes dx. And this is your formula. This is what we need to know. This is how you find the length of any curve. You're going to integrate the square root of 1 plus the derivative squared dx. So let's go take a look at a couple examples of this. All right, here I've got the curve y equals the square root of x. It's a bad y-axis there. Y equals the square root of x, and we want to find this length over the interval from 0 out to 4. So we want the length of that curve. So our formula is the integral of the square root of 1 plus dy dx squared dx. So I need to find what the 2 points are on the integral, so that's from 0 to 4, and I also need the derivative of this function. So I need to identify that. So the derivative of this is 1 over 2 square roots of x. And the derivative squared, which is important, is going to be 1 over 4x. So my arc length is going to be the integral from 0 to 4 of the square root of 1 plus 1 over 4x dx. And that I'm going to type on my calculator, and I get that this is about 4.64678, and that answer right there is E. Let's do another one. The arc length of sine of x over the interval from 0 to pi over 6. So here's our sine graph, and we want to go, let's see, that has a maximum right there at pi over 2. So I'm just looking at this small little part here from 0 to pi over 6. So my formula is the integral from a to b of the square root of 1 plus the derivative squared dx. All right, so if my function is sine of x, my derivative is, do you remember, is cosine. And the derivative squared will be, well, cosine squared. So my arc length is going to be the integral from 0 to pi over 6 of the square root of 1 plus cosine squared. And I will need my calculator for that, and my calculator tells me that this answer is 0.724147. So that works out to be B. Oh, look, all these are going by 3 decimal places, right, Nina? Much love. Heart. Okay, let's do one last example, which comes from an AP test. And this example is similar to what we've been working on the last couple of days. We've got a region bounded above by the graph of e to the 2k and below by the graph of y equals 0. And then we've got x equals 0 and x equals k. So here's our region. And we want to write, but not evaluate, an expression involving an integral that gives the perimeter of R in terms of k. So we want the perimeter. So let's do the easy parts first. My perimeter is going to be the left-hand side, the bottom, the right-hand side. Those are easy to add up. This y value is 1, so that first length is 1. Plus, this value out here is going out to k. So the base has a length of k. Plus, the right-hand side has a y value of e to the 2k. So those are easy to count. But what I can't count is the length of this curve right here. And that's where I'm going to use my formula. So this is the graph of e to the 2x. I might have said e to the 2k earlier. That's just where it stops at k. This is the graph of e to the 2x. And so my derivative of e to the 2x is because the derivative of e to the u is e to the u du, so that's 2e to the 2x. And my derivative squared is 4e to the 4x. Remember, if you raise a power to a power, you multiply those, so 2x times 2 is to the 4x. So here is my formula for that. The integral, and we're going from 0 to k, of the square root of 1 plus the derivative squared dx. And that is my answer to that question. So tomorrow in class we're going to practice some arc length questions, and then on Thursday we're going to review, and Friday we're going to have our test. So I will see you guys tomorrow.